Howdy, this is your friendly neighborhood physics teacher here, and we're going to talk about collisions. But just a little reminder of what we've already talked about. So we've talked about momentum, and if you remember, momentum is just inertia in motion. So to see which qualities affect momentum, you have to think about the equation. Now, your equation for momentum is momentum equals your mass times velocity. Again, it's inertia. That's why they're both yellow. In motion. That motion means velocity. Back up. Okay. And then we talked about impulse. So impulse, to see which quantities affect impulse, again, you have to look at your equation. So your impulse is just equivalent to your change momentum. Basically what that is how does your velocity change? Does it speed up or does it slow down? And what causes that change? So it'd be your force and how long it takes for that force to affect the object. What we're going to be learning about today is applied concepts of conservation of momentum. So we're going to talk about elastic collisions. So that right here, that's when two things stick together. And we're going to talk about inelastic collisions, or elastic collisions, where things bounce off. That's the main thing we're going to talk about today. I just want to do a quick overview. So collisions in one dimension. We're not going to do 2 dimension, so it's just going to stay 1 dimension. So you're good, no angles. So conservation. Just like conservation of energy, we have conservation of momentum also. And so it's the preservation from loss. So you try to keep the system from losing momentum or losing energy. So conservation of momentum kind of leads to an equation. So that basically, I guess, like conservation of energy, that total amount of energy into a system has to equal the total amount of energy you get out. It's the same thing for momentum. The total amount of momentum you put into the collision has to be equal to the total momentum you get out of the collision. And usually when you have a collision, you have 2 objects. So you have to take the momentum of object A and the momentum of object B. Now, it says before the collision. So you have to think about what is their momentum before the collision, both of them, and you just add those 2 together. And that has to equal the momentum of A and B after the collision. And you can break that down. You can spread it out because momentum is just mass times velocity. And you just use these little labels to say, this is specifically the mass for ball A, this is specifically the mass for ball B, velocity, and so on and so forth. And the key thing, though, just to keep everything straight, this section, the one that's before the equal sign, is your before the collision. What's after the equal sign is after the collision. So you really do have to break up the situation into 2 different parts. What happened to the object? What was the object doing before they hit? What were the objects doing after they hit? And this is for an elastic collision. So let's look at this rifle. So again, we're going to do momentum before the collision and momentum after the collision. So let's look right here. So this is before the collision. How much is the gun moving right now? So hopefully you see that the velocity of the gun is 0. How much is the bullet moving right now? Hopefully you see that the velocity of the bullet is 0. So before the collision, and the collision is you firing the gun, so before the collision, nothing's moving. Your velocity is 0. Now the collision happens, and then it goes. So now, both the gun and the bullet move. Which one do you think is moving faster, though? Yes, hopefully you said the bullet. The bullet is moving faster. And again, it's relative size. The bullet has less mass, so it's able, because they have the same momentum, the bullet has less mass, so it's able to go faster. The gun, which has more mass, even though it has to have same momentum, is not to be able to move very fast. So if we break that down into equation form, so you have so this is the mass of the gun, and we already said that before the collision, the gun's not moving. This is the mass of the bullet. We already said before the collision, the bullet's not moving. So after, then you have the equal sign, and so everything is after the collision. So again, this is before, this is after. Now, does the mass of the ball and the bullet change from point A to point B? No, it doesn't. So again, you just mass of the gun, mass of the bullet. Why would the velocity of the gun be negative right here? Why is that negative? Let's go back. Let's go back so we can see it real quick. Oh, not that far back. This far back. Which direction is the bullet going? The bullet is going to the right. Which direction is the gun going? The gun is going to the left. So that negative there is just telling us to the left, to the left, to the left. And then our velocity of our bullet is positive because it's going to the right. There we go. Nope, keep clicking on that. Now, 0 times anything gives you 0. And so you're just left with 2 times -1, and then 0.01 times 200. So you just get a -2 plus 2. So your 0 equals, so basically you're getting 0 equals 0. Both sides end up coming to 0. But the biggest thing I want you to focus on is, because this is the gun, right? And this is the bullet. Their magnitudes. Now, everyone kept asking what the word magnitude meant. Remember, magnitude just means number. Momentum is a vector, so it has magnitude and direction. But if we're asking for the magnitude, we're just asking for the number. But the number of the gun, the number of the bullet is the same. It's just the direction that's different. So there we go. So for inelastic, so that was an elastic collision. Two things separating. An inelastic collision, or a sticking collision, is when two objects go at each other and they stick to each other. So if two objects stick to each other, that means they're moving at the same velocity. So we don't have to worry about two velocities after the collision. They're both moving at the same velocity. So that's why you just add the masses together, because they literally stuck together. And you only have one velocity on the after side. So that's the only big difference between inelastic and elastic collisions. Elastic collisions, you're still dealing with two separate objects, so you still have to do two different velocities. Inelastic, the objects have stuck together, and so you only have to deal with one velocity. So these are little animations just to kind of give you, so you can visualize what's going on. That's all this is. It's just so you can visualize. We'll move through these pretty fast. So you have cart A that goes and moves and sticks to cart B. Cart A and cart B have the exact same mass. Now, if you remember at the beginning, cart A is moving, cart B is not. It goes and sticks to cart B and it makes it move. so car A is moving pretty fast, but then as soon as it hits B and drags B along with it, it slows down. Why does it slow down? Hopefully you say it slows down because now it's dealing with double the mass. So you sit there and do your little calculations here. You get that your velocity is just 1/2. You started out with 1, you double the mass, so now you get 1/2. So right now we're just comparing. We're just looking at relationships. So again, we have a blue car that's not going to be moving, but instead of 1 kilogram, it's going to be like 2 kilograms because we have another mass on top of it. And then we have the red that's going to be moving, and it's at 1 kilogram. So let's see what happens here when the red moves and hits. And they start moving together, and I didn't do a really good job of animating it, but it should be moving a whole lot slower. And again, the reason for that is you started out with 1 meters per second with 1 kilogram, but now we're getting to 3 kilograms. Once that red picked up blue, it's to 3 kilograms. So your velocity is going to decrease and become 1/3. So what's going to happen here? This little people talking is, if we were actually in class, I would play it for you, and you would then turn to your discussion partner and you would discuss. So turn to grab a younger sibling, grab a cat, grab a dog, grab a stuffed bunny, a water bottle, I don't know. So get ready to discuss something. If the non-living things start talking back, we have been in this world too long, in this situation way too long, because I swear my water bottle is talking back to me. So here we go. So it hits, they stick, and they start moving. Now let's replay that. So everything we showed before, it was only the red that was moving at the beginning, not the blue. But now we have both of them moving towards each other. They're moving towards each other. They do stick. So this is an inelastic collision. But why does red make blue go its direction? So why did red win instead of blue winning? Hopefully you said it's all about the mass. Because think, red is like 2 because it has 2 on there. Blue is 1. It's just like football. The reason you put the big guys in front to protect the little ones is so the big guys can push people out of the way. I know that's a very simple version. I'm sure my people that actually watch football are groaning right now. But that's a very simple version of it. So if we look at it, we have our mass of the red car, which is 2 because there's 2 things on it, and it was moving at 1. The mass of the blue car, and again, that negative right there was just telling me it's moving to the left, like the arrow on the blue. And when it's stuck together, it now became 3. So it became 3. So your velocity is still 1/3, but it's 1/3 in the positive direction. And the reason it's 1/3 in the positive direction, again, you have big guy versus small guy. Big guy's going to win, and most of the time in a pushing contest. So again, this is just looking at an elastic collision again. I don't know why this is down here. And because elastic collision. So those were all inelastic collision examples. Now we're going into elastic collision examples. So again, we have red and blue coming at each other, same mass, but they're going to hit and bounce off. Now, it's hard to tell, but red's moving slower than blue at the beginning. I didn't make it dramatic enough, but blue is moving faster, red's moving slower. They hit, but what happens after they hit? Red starts moving faster and blue starts moving slower. So it's kind of like one of those, they just completely flip. So they're both 1 because there's nothing sitting on top of each other. So if the red was moving at half, the blue was moving at -1. Remember, negative just means direction. what would be the two velocities after they hit? Now, I will tell you this, that I will not make you solve for both velocities. I'll only make you solve for one of the velocities, but I'm just kind of leaving both blank so we can look at how that's affecting it. And what you'll see is that the two velocities just flip. Red starts moving at a 1, just going a negative because it's going the opposite direction, and your velocity, your blue one is 1/2. Because in an elastic collision, energy is conserved also. In an inelastic collision, energy is not conserved. It loses energy to something because that takes energy to get them stuck together. And usually it's losing it through thermal or sound or something. But for an elastic collision, energy is conserved. So it hits, the red stole some of the blue's energy, and they move on. But together, if you added up the energies, it would still be the same. So now we have the red moving and the blue not. So what do you think is going to happen here? If energy has to be conserved for an elastic collision, what's going to happen? Let's find out. Boop. So red gave all its energy to blue. Red gave all its energy to blue. And it's because it has to be an even transfer. They have the exact same mass. So when they hit, it just keeps moving. Hopefully you remember the Newton's cradles when we did energy. The reason that you could pull one back and it hit and only one goes up is because, again, you're showing conservation of energy, but you're also showing conservation of momentum there. Because if you pulled up two would launch off. And it's, again, you're conserving that momentum. Now we have pretty much the same situation, but we have double the mass on red. What do you think is going to happen now? Let's find out. Kaboom. So yeah. So blue took all the momentum it could handle. It's like, I got this. But there's still some left over for red to be able to move. Why do you think that was? Hopefully you said it was because they don't have the same mass. So blue was only able to take so much until it was like, I can't take anymore. I'm out of here. Peace. And so red was left with still a little bit more. So that one is still got to be like evenly kind of transferred to the balance to the two things. And so you get something that your blue took about 4/3 and your red only took about 1/3. That should be 3/4, not 4/3. I flipped that. That should be 3/4. I am talented. Woohoo! Okay. So continue on. But now we have red moving and it has less mass than blue. So what do you think is going to happen here? Boop. Ooh, so why did that happen? Let's play that again. So it went up and hit. So why do you think that happened? Why didn't it just hit and stop? The reason is because it did transfer some energy, so it is going to move, but it kind of acted like a wall because it was so much massive then, and so it was able to hit and bounce back. So we look at it mathematically. You're looking for that two velocities. Again, you have 1/3 negative because it's going back, and then you have 2/3 going forward. And it's still that, it's got even of 1. And again, because that bigger object kind of acts like a wall, so it just bounced off and kept moving, but it gave it some energy. Now, what I'm about to show you now is completely extra. So if you're done with notes, you're like, I get this, I'm cool, you can turn off the video at this point in time. If you want to expand, this is the last slide on the PowerPoint I'm about to go over. I know several of y'all were asking me questions over it, so I'm about to step through the last slide. This is extra information. You are not going to have any questions over this. So if you're like, I'm done, peace out, have a wonderful day. But for my ones that want to do a little bit extension, please stay with me and enjoy the mathematical craziness we're about to do right now. So conservation momentum. This is an elastic collision, so we're going to stick with our elastic equation. Again, it looks just like what we just did before. But instead of just kind of guesstimating our velocities like we have been, let's actually prove that these velocities are true. Now, you can't solve an equation that has two unknowns. It just doesn't work that way. So basically what I did here is I chose to solve for my velocity of the red car. So all I did is I maneuvered things around so I can get my V1 equal to whatever it would equal to. But again, I still have two unknowns. That doesn't work mathematically. But this is an elastic collision. Since it's an elastic collision, I know that energy is also conserved. So I can go back through my notes. Oop, look, there's my conservation of energy equation. In this case, we're just dealing with kinetic energy. There's no potential energy. We're just dealing with kinetic. Kinetic energy is 1/2 mass times velocity squared. So you have to think about the kinetic energy for the red, kinetic energy for the blue in both situations. Remember, before the collision and after the collision. And so we have the red one was moving at 1, the blue wasn't moving at all, and we have two unknowns. But we can solve. Oh, well, we're simplifying, then solve. There we go, solve now. Thank you. So basically what I did is I took what we solved for V1 over here, and all I did is I plugged it in. Plug it in, plug it in. And y'all are too old to know that commercial. Grr. Too young, too old. Okay, so too young to know that equation. But you just plugged it in. And now, oh look, we can solve for V2 now because we only have one unknown. So now it just turns into algebra. Dun, 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 dun. Magical algebra. Poof. So we get that our V2 is 2/3. So now what we can do, we can take this 2/3 and plug it over here. Plug it in, plug it in. And we can solve for our V1. So that's when you're given two unknowns like that, you can actually, and it's in an elastic collision. It doesn't work for an inelastic, but you wouldn't have two unknowns for an inelastic because you only have one velocity after the collision. But for an elastic collision, you can actually do conservation of energy and conservation of momentum. They work hand in hand. So hopefully you have that helped and you have a wonderful rest of the day. Remember, you are loved and appreciated. Bye.